Welcome to Talk Tensors. We're diving into a really interesting paper today. Graph-Grounded LLMs, leveraging graphical function calling to minimize LLM hallucinations.
Yes, it tackles a problem that's, well, increasingly important. How do we get large language models to handle graph structures reliably?
Exactly. Graphs are everywhere, aren't they? Social networks, robotics, understanding scenes, you name it.
And graph theory itself gives us these powerful, optimized ways to solve problems related to them.
But LLMs, despite all the progress, they still struggle sometimes. Hallucinations, math errors.
Which is a big blocker for using them in anything safety critical that relies on graphs.
So this paper proposes something called graph-grounded LLMs. That's our focus today.
Right. The core idea, essentially, is hooking up a graph library to the LLM using its function calling abilities.
And the promise is, what? Fewer hallucinations, better accuracy on graph problems?
Pretty much. They show some really compelling results on the NL graph benchmark, which we'll get into. It seems to significantly improve things.
Okay, so let's unpack that. LLMs are getting better and better at language. We know that.
Absolutely. Generating text, understanding context. Incredibly powerful.
But ask them to reason about, say, the shortest path in a network described in text.
That's where things can get shaky. They might misunderstand the structure, infer connections that aren't there, basically hallucinate.
Which, again, is fine for some tasks, maybe, but not for planning robot movements or analyzing critical infrastructure.
Definitely not. You need precision there. And that's where traditional graph algorithms shine. They're designed for exactly this kind of structured reasoning.
So the challenge is bridging that gap, the LLM's language skills and the algorithm's logical rigor.
And this paper's approach is pretty clever, giving the LLM a toolkit.
A toolkit, like actual software tools?
Sort of. A library of graph functions, things like find shortest path, check connectivity, build graph from nodes and edges.
Ah, I see. So the LLM doesn't try to calculate the shortest path itself.
No, not directly. It recognizes, okay, this problem needs a shortest path calculation, and then it calls the function from the library.
It delegates the computation, basically.
Exactly. It delegates the heavy lifting, the parts requiring strict mathematical or logical execution, to code that's known to be correct and efficient, like using networks or a similar library.
That makes a lot of sense. You use the LLM for what it's good at, understanding the natural language query.
Interpreting the goal, maybe figuring out which function to call.
And then you use the dedicated graph library for the actual graph operation.
Right. It keeps the LLM in its strength zone language and high-level reasoning, and leverages decades of computer science work on graph algorithms for the computation.
So for our listeners working on, say, knowledge graphs or social network analysis, this could be quite impactful.
Hugely. Imagine describing a complex network in text and having the LLM reliably build it and answer questions about it using these grounded functions.
Less guesswork, more reliable answers.
That's the goal. And the NL graph benchmark results seem to back this up strongly.
Okay, let's get into the paper's details then. How did they structure their work?
Well, they start by acknowledging, the expanding use cases for LLMs in graphy domains.
Like the robotics and autonomous driving examples you mentioned earlier.
Right, and structured reasoning, knowledge probing, even things like node classification in graph neural networks.
But they quickly pivot to the challenges.
Yes. They point out that LLMs struggle to map text descriptions accurately onto the conceptual space of a graph. They get confused by complexity, find spurious correlations in the text.
Instead of focusing on the actual graph logic.
Precisely. So they propose this hybrid approach. LLM for the high-level stuff, traditional software, the graph library for the intense computations.
And the mechanism is function calling. How does that work in practice?
The LLM is given the problem description, but also a set of tools described in JSON format. Each tool is one of the graph functions.
So the LLM sees, okay, I have a function called find shortest path that takes these arguments.
Exactly. The paper mentions they built a library with 29 common graph functions using networks. Things for construction, manipulation, pathfinding, flow, components, the usual suspects.
And it uses something called zero-shot chain of thought.
Yeah, meaning it tries to reason step by step using these functions without needing prior examples of that specific task. It might call one function to build a graph.
Then another to check for cycles, maybe?
Or another to find the path, yes.
Okay.
It can be an iterative process. A function manager handles the calls, executes them using the library, and feeds the results back to the LLM.
So the LLM might ask, build a graph with these nodes and edges. Gets confirmation. Then asks, Okay, now what's the distance between A and Z?
That's the flow. It allows the LLM to build up the solution piece by piece, grounded in actual graph computations at each step.
They must have some examples of where this makes a difference.
Oh, yeah. They have a good one with a social network. A standalone LLM is asked how many steps for a message between two people. Gets it wrong, invents connections.
Hallucinates the path.
Right. The graph-grounded version, it calls functions. First to build the graph correctly from the description, then to calculate the shortest path. Gets the right answer.
Makes sense. Any others?
There's another with a disconnected graph. The standalone LLM tries to find a path between two nodes that are in separate components.
And probably just makes one up based on the text.
You got it. The graph-grounded system calls the relevant library function, which correctly reports that no path exists, because the library knows about graph components.
So it really highlights how grounding prevents these specific kinds of structural errors.
Exactly. And that brings us to the NLGraph benchmark they used.
Right, you mentioned that. How comprehensive is it?
It's pretty thorough. Over 6,000 problems across 8 different graph reasoning tasks.
What kind of tasks?
Things like basic connectivity, cycle detection, topological sort, shortest path, max flow, bipartite matching, even checking Hamilton paths and evaluating GNN reasoning. So a good spread of complexity.
And the results, you said they were significant.
Very. Table I in the paper shows the comparison. The standalone GPT-4 model struggles quite a bit on many tasks as complexity increases.
And the graph-grounded version.
Near 100% accuracy on most of them. It's a night and day difference for many tasks.
Wow, okay. That's quite a validation.
It really is. Now, they do note it takes a bit longer computationally.
Because of the back and forth with the function calls?
Presumably, yeah. Multiple calls add overhead compared to the LLM just trying to generate an answer in one go. But the trade-off for that massive accuracy boost seems worthwhile, especially for reliable applications.
Did it still fail sometimes? What went wrong in those cases?
A few things. Sometimes ambiguity in the original prompt could still confuse the LLM about which function to call or how to interpret the task.
Ah, so the initial natural language understanding part is still key.
Absolutely. Garbage in, potentially still garbage out, even with the tools. There was an interesting case with topological sort.
What happened there?
The initial prompt was something like, can all the nodes be visited? The LLM apparently confused this with the Hamilton path problem sometimes.
Oh, right. Similar wording, but very different graph problems.
Exactly. When they clarified the prompt to, can all the nodes be visited in a valid topological order, the accuracy shot up.
So prompt engineering still matters a lot.
It does. The other main failure mode was context length limits, especially with really large graphs where describing the graph and the function calls might exceed the window.
That's a familiar limitation for LLMs.
Yeah, suggests you might need techniques like retrieval augmented generation, maybe, for truly huge graphs to dynamically fetch relevant functions or graph parts.
They also mention Hamilton path being NP complete.
Right, just noting that their simple backtracking implementation for that specific very hard problem isn't efficient, which isn't surprising. It highlights that the quality of the library functions matters too.
Okay, so the grounding helps immensely with graph logic, but prompt clarity and context limits are still factors.
That sums it up well. Yeah. And they also showed a practical application.
The disaster response scenario.
Yes, it's a nice demonstration of how this could work as a decision support tool. The LLM takes in reports, collapsed buildings, fires, victim locations.
Okay.
Uses custom functions, maybe get environment data, then uses its graph library to build a map, represent hazards.
And then plans routes for rescue robots.
Exactly. Finding safe paths, avoiding debris or fires, prioritizing victims based on location and maybe reported condition. It can answer queries like, how close is robot A to survivor 3, using the graph functions.
And it can adapt if things change, like the fire spreads.
That's the idea. New information comes in, the LLM updates the graph representation using function calls, and then replans or answers queries based on the updated graph. Much more dynamic and reliable than an LLM trying to track all that state internally.
That really does paint a picture of the potential. But they also list limitations, right?
They do, which is good. They note it's designed for implicit graphs and text, so adapting to other domains needs new functions.
Building that function library takes effort.
Significant effort, yeah. Coding, testing, handling edge cases, the paper acknowledges. That's on the user.
Plus the computation time and context window usage we mentioned.
Right. And having too many tools could potentially confuse the LLM, leading to wrong function calls.
So there are trade-offs. It's not magic.
No, but it's a very promising direction for making LLMs more reliable in structured domains.
Thinking historically, this feels like a blend of old and new AI, doesn't it?
It really does. Symbolic AI, GOFAI, was strong on logic and planning, but brittle with real-world ambiguity. Deep learning excels at perception and language, but struggles with symbolic reasoning.
And graph theory was always a pillar of that symbolic approach.
Absolutely. So this work is like marrying the LLM's world understanding and language flexibility with the rigorous, provable methods of graph algorithms.
It's a hybrid system, leveraging the strengths of both. We've seen hybrid approaches yield breakthroughs before in AI.
Often, yes. Combining paradigms can overcome individual weaknesses. This feels like a natural progression for tackling complex tasks that involve both understanding unstructured information and reasoning over structured relationships.
So boiling it down, the key innovation is that tight integration. LLM function calling plus a dedicated graph library.
Yes, that iterative process where the LLM uses the library as a computational tool to ground its reasoning.
And that grounding dramatically cuts down hallucinations for graph problems.
The NL graph results are pretty strong evidence for that.
And the disaster response example shows the potential for real-world, high-stakes applications.
Definitely. Think robotics, logistics, maybe even bioinformatics or network infrastructure management. Anywhere reliable reasoning over connections is critical.
It could even make complex graph algorithms more accessible, letting people query them using natural language.
That's another interesting angle, yeah, democratizing access.
Okay, great overview. Let's shift gears now to our novel notions segment. Based on this paper, what's a speculative, forward-looking idea that springs to mind?
Okay. One direction could be autonomous graph library evolution.
Autonomous evolution. You mean the LLM improving its own tools?
Kind of, yeah. Imagine the graph-grounded LLM encounters a new type of graph problem its current library can't solve efficiently, or maybe even at all.
Okay.
Could it potentially propose a new function? Maybe even generate the code for it, based on its understanding of graph theory and the problem.
Whoa. So it identifies a gap in its toolkit and tries to fill it.
Exactly. It might generate a Python function definition, for instance. Then perhaps it could use another tool, maybe an automated testing framework, perhaps even one guided by another LLM, to check if the new function is correct and efficient.
And if it passes the tests?
It gets integrated into the library. The LLM essentially learns and expands its own capabilities over time by building better tools for itself.
That feels very meta. What makes you think this is plausible?
Well, the paper's authors themselves mention automated library modification as future work. And we're seeing LLMs get incredibly good at code generation and understanding formal systems. It combines those strengths.
The impact could be huge, right? Systems that adapt to new problems without constant human reprogramming.
Potentially. You might even get LLMs discovering novel or more efficient algorithms through this kind of autonomous exploration and testing cycle. That's maybe further out, but intriguing.
What's the likelihood near term versus long term?
Near term, probably low. Reliable code generation and especially verification are still major hurdles. But long term, as those core capabilities improve, I'd say medium to high probability we see steps in this direction.
Fascinating. Okay, that's one cool idea. Got another.
How about hybrid graph test reasoning for knowledge discovery?
Okay, break that down. What's the hybrid part?
So instead of just working with graphs explicitly described or provided, imagine the LLM reading large amounts of unstructured text, say scientific papers, news articles, reports.
And doing what with it?
Identifying entities and relationships within that text, and then using its graph-grounded functions to dynamically build a knowledge graph from that information.
So it constructs the graph from the text first.
Yeah, right. On the fly. Then you could ask it complex questions that require both understanding the nuances of the original text and reasoning over the structure of the graph it just built.
Give me an example.
Maybe you feed it a ton of biomedical literature. It builds a graph connecting genes, proteins, diseases, drugs based on what the papers say. Then you ask, what are the potential indirect pathways linking gene X to disease Y, considering mechanism Z mentioned in recent papers?
And it would use its graph functions on the dynamically built graph to answer that.
That's the vision. It bridges the gap between pure text understanding and structured graph reasoning for knowledge discovery.
Why is this a compelling next step?
It connects this paper's focus on reliable graph reasoning with the huge field of knowledge extraction from text. LLMs are already being explored for knowledge probing. This adds a robust reasoning layer. Think about domains drowning in text, science, law, history. This could unlock insights hidden in the connections.
What are the hurdles or maybe overlooked points there?
The main hurdle is reliable information extraction from text. Text is messy, ambiguous. Getting the graph construction right from noisy text is hard.
Sure, extracting accurate relationships is non-trivial.
But as LLMs get better at that extraction, this becomes more feasible. An overlooked implication. Maybe these dynamically built graphs could uncover connections missed by slower, manual knowledge graph curation, and the graph could evolve as new text comes in.
Continuous knowledge synthesis, almost.
Sort of, yeah. Pretty exciting potential, medium probability in the near term due to the extraction challenges, but high in the longer run, I think.
Two very thought-provoking notions there. And just a reminder to our listeners, these are speculative ideas, food for thought, based on the research.
Absolutely. For entertainment and inspiration only.
So wrapping up our deep dive today, the big takeaway really is that these graph-grounded LLMs offer a significant step forward for reliable AI.
Definitely. By grounding the LLM's language abilities in the proven logic of graph algorithms via function calls, they mitigate those problematic hallucinations on graph tasks.
It's a powerful hybrid approach, showing real promise on benchmarks like NLGraph and in potential applications like that disaster response scenario.
It opens doors for using LLMs more dependably in robotics, logistics, network analysis, anywhere structured relationships are key.
We really encourage you, our listeners, to check out the paper itself for all the details on the methodology and results. It's linked in our description.
It's a valuable read for anyone working at this intersection of LLMs and structured data.
And to leave you with a final thought, as we see more integration between neural approaches like LLMs and symbolic systems like graph libraries, how might this synergy reshape our ability to tackle truly complex, multifaceted problems in the real world? Something to ponder.
Indeed. The future there looks very interesting.
Thanks for joining us on Talk Tensors.